So here I'm gonna write the final formal equations that we're gonna be coding. Exactly these equations we're gonna be using in Python code to make the neural network. So this is forward pass. Okay, let's see. A1 equals to sigma of Z1. Okay, and I can write Z1 equals to, we're gonna be careful with the dimensions as well. So here W1 dot transpose dot X plus B1. This is gonna be the equation for the Z1, as you know. Okay, let me do this real quick. All right, here we know dimensions of W1, it will be 16,784. I mean, with the transpose, X will be 784,1. All right, this is gonna be 16,1. So you can see how the dot product is coming together here. Similarly, for A2, it's gonna be sigma of Z2, and Z2 will be W2 dot transpose dot A1 plus B1. All right, let's look at the weights. The weights will be 16x16. Even if we transpose it, it will be 16x16, and A1 is nothing but 16,1. B1, B2, my bad. This is B2, and that's 16,1 as well. All right, and Z3 equals to W3 dot transpose dot A2 plus B3, and let's write down the equations real quick. It's going to be 10,16. It's going to be 16,1. And it's going to end up 10,1. This is a plus. Okay, be careful here. That's a plus, and this is a dot product. All right. This is for our forward pass. Okay, I want you guys to take a screenshot of it. I'm going to put it up on coding. But yeah, this is going to be our forward pass. Now I'm going to write an equation for our backward pass. So we know the cost is the average 1 by k, as k is the number of images. We're going to be using that when we're using the whole data set. So number of images into O minus y whole square. Okay, so derivation of that will be k O minus y. Okay, we can write it as this, and now let's see what DW1 was. I'm not going to derive it again. Sorry, DW3. I'm not going to derive it again. I'm just going to write it with matrix matching. Okay, so before this, let me write DZ3. DZ3 is nothing but DC, element-wise multiplication of sigma dash of Z3. All right, and here it's element-wise multiplication. This is 10,1. This is 10,1, and resulting will be a 10,1 as well. All right, the W3 equals to, we're gonna write A2 dot of the Z3 dot transpose. Okay, that's what DW3 is going to be. Let's look at the dimensions real quick. This is going to be 1,10, and A2 is 16,1, and W3 16,10. All right, they match. The dimensions match. DW3 is going to have the same dimensions as W3. All right, let's go with DB3. It's nothing but DZ3. Okay, It's actually sum of DZ3, and it's gonna have the same, sorry, it's 10,1. Yep, and this is also 10,1. All right, that is for W1. All right, what about DZ? Let's come here. DZ2. DZ2 is gonna be W3 dot DZ3 into, the star is element-wise multiplication here. Sigma dash. Sigma can be anything. I'm gonna use rel u, by the way, here. Rel u, because I want to have some difference. I'm gonna talk about rel u right after I derive this equation. So Z2. Okay, let's write out the DZ. Well, we can write out the dimensions here. W3 is nothing but 16,10. And DZ3, we can see here 10,1. So resulting will be a 16,1, and this is 16,1 Z2. So 16,1 element-wise multiplication. This is gonna give us 16,1. All right, let's go DW2. DW2 will be A1 dot DZ2. Okay, that's what DZ2 dot transpose. Okay, that's what it's gonna be. And let's write out the 16,1 for this. This should be 16,16. And this, what is this? 1,16, since it's transposed. Okay, they do match. Okay, so we know the equation is correct. 2 is nothing but sum of DZ2, and this will have the 16,1, and this will also have 16,1. All right, before I move on to write the actual equation for the backward pass, I'm gonna explain what the rel u is. Rel u is a function which takes in x and gives out the pot if x is less than 0 or equal to 0, it gives out 0. If it's greater than 0, it gives out x. Okay, so this is how the function looks. This follows this line. Let me use red. Follows this line and this. Okay, that's what rel u is. Rel u function. It's you remember what it does? It squishes it into the node. That's what it's an activation function. There are a lot of activation functions. Okay, so rel u is one of them. I'm gonna be using that for the second and first layer. For the third layer, we're gonna be using sigmoid. All right, let's focus here now, and let's write DZ1 real quick. Okay, what is DZ1? DZ1 will be W2 dot DZ2 element-wise multiplication sigma dash. Actually, it'll be rel u dash. I'm just writing sigma for now, but it's going to be rel u derivative because we're going to use rel u here instead of sigma. But I'm just writing it like this for now because that function couldn't mean anything, okay? All right, let's see. W2 is 16,16, right? What is DZ2 right here? 16,1. We dot it, we get 16,1. And what is Z1? Z1 is 16,1, and we'll have resulting 16,1 right here. Okay, and DW1 equals to? DW1 is nothing but x dot DZ1 dot transpose. All right, let's find W1 is nothing but 784,1. comma 1. This is 784 comma 1. Dot DZ1 is 1 comma 16. DZ1 transpose, right? So this will give us this. All right, and finally db1 equals to summation of dz1. All right, these are the equations. I'm gonna take a screenshot and I'm gonna put it right next to the block when I'm coding. All right, so this is where I got the dataset from. I'm gonna leave a link in the description, and let's get started. I was gonna code from scratch, but I don't really have time for this, so I'm gonna just try to get through it as soon as possible, and I'll try to explain all the code as much as I can, as fast as I can, I guess. Okay, here we're importing 3 libraries. Pandas, we're just using pandas because it's in CSV, and we're just using it to read the file, and we're converting it to NP array right here. So that's all the pandas does, okay? And right here, data type train, this is how it looks. So you see the first row is the labels, and the rest of them are zeros. So that tells me that this column, the first column is an image, the second column is an image, the third column is an image, okay? So after that, we're gonna split it into X test, Y test. X will have the image, Y will have the label, okay? And what else? Okay, what we're doing here, why did we do this? Because apparently X train, as we thought, like our assumption was the values of X on the first input layer nodes were ranging from 0 to 1, right? But it was actually ranging from 0 to 255. So we divided it by 255, the whole set, so it will range from 0 to 1. Here we just normal input. Here we're defining a network. So this is how it looks. Input size is nothing but 784 right here, you can see, and 16 is our hidden layer size. So, and output is 10. So you can see here we're just randomizing, we're taking random values here. So I did this so we can just see how W1 W2 looks. Oh no, my bad. All right, I'm gonna have to execute it one at a time, I guess. Okay, we can do this. All right, moving forward right here. All right, let's look at what W1 is. We're just putting in random values, so we'll have random values, and I'll talk about this part right here. This is a special type of initialization where we take those random values and then we multiply it with the square root of 2 by the input, the first, the left side's layer number of nodes. One shape. Okay, look at this. W1 shape has this. We had these initialized on our paper as well. And let's look at what W1 is. So W1 looks like this. See, look at that. And it's just random values. Okay, let's see np.max. So what's the maximum value of this? np.max. Max of W1. I'll give us the maximum value. Okay, the maximum value of W1 is 0.17. And np.min of W1 is minus 2.1. Okay, so W1 currently ranges from this to this, and we can see for W2 as well 1.1. So these are random values, by the way. So, and for W3 it ranges from 0.8 to minus 0.8, close. Okay, and these are all B1, B2, B3 are zeros. We can check the shapes. I'm pretty sure the shapes are gonna line up because here we have initialized shapes as accordingly, like input comma I didn't mean to do that. Input comma hidden shape 1, and we know input is 784, hidden shape is 16, so it's going to be 784 comma 16. The second one's going to be 16 comma 16. The third one's going to be 16 comma 10. Okay, so that's how that is. And these are the sigmoid function that I told you about, which squishes it between minus 0 to 1. This is the derivation of sigmoid. I can do that on paper. I'll probably do it on paper and show you, maybe. I'm not really sure. This is rel u. I told you this is if x is negative or 0, it gives 0. If x is positive, it gives positive. And this is the derivation of x. And this is one hot encoding of y. Okay, this turns, like currently here, if we see, we haven't run that cell yet. So to see what y is, we're going to be using y train, right? Look at y train. It looks like this, right? We want this to look like that shape. Let's look at the shape as well. It's going to be 1,6000. Okay, it has one row and it has 6,000 columns. So yeah, so this is how it looks. So what we want is this 5 to become like a column of where the fifth input should be 1 and everything else should be 0. So we want the shape of the y will be, after we're done one hot encoding, the shape of the y will be 10, 60,000, not 1. Okay, so it's going to be 10. So that's what we're doing here. And I've already explained how one hot encoding works, so I'm not going to go into that anymore. And let's look at the forward pass. I'm going to put up an image on the top right or somewhere so we can match our equations. So you can see here, forward pass, it takes in weights and it takes in x, which is our image, and these are the equations that we derived, and it returns z1, z1, z2, z3, a1, a2, and output. Similarly, did we run it? All right, similarly, all right, right here we can see y equals to 1 out of y. So we've made the y as a column vector which matches the dimension of O, so we can subtract it right here. 1 by k. Why do we do 1 by k? Because we're taking the cost function across all the images that we have in there. Okay, so this is the derivation of cost function, just 1. Okay, with anything, if you do it, this will be the initial derivation. So here we're doing, so here I've written, oh my god, my variables. Okay, maybe we have different variables in there. I'm gonna change the variables real quick here. So it was a CD for this, and it was DW1, DW3, I mean, my bad. It was D this, and CD. Okay, everything else the same. I'm gonna change right here as well. DW2, DW1, D, and it's gonna return D. I'm bad at naming variables, but yeah, okay. This looks exactly as our equations, and here we are. Oh, I have to do this for everything now, huh? That's sad. But either way, as I was saying, here we are updating the weights. We could have done this in actually, what I'm gonna do right now is I'm gonna put this part of the thing the updating weights, I'm gonna put it in the I'm gonna put this right here actually. And yeah, I just want to return W's. I don't need this. Okay, yeah, this looks much better. Okay, and that's it. Now here we're defining a prediction. So here we're done. This is our forward pass, this is our backward pass. All the heavy lifting is done. We've already coded what we needed to code. It's not working. Okay. And now we're getting predictions. So we're taking the max of the output here. And these are just simple code you get for accuracy for models. And here we're, okay, this is where we define train. So I'll walk you through everything what's going on in this low block. So here we're getting W1, W2 weights from this initialization, okay? We haven't initialized it yet, so okay, how about you forget about this for now? Like, remember that we have a block train, okay? I'll get to it. I need to change it actually. I need to do this X, and this is my output. Y. We don't have anything called update weights. Okay, that looks good. All right, why are you red here? I don't know. Okay. Let me just execute it and I'll walk you through it in a second. All right, so here we get W1, W2, W3 from train, right? So what's happening in train? First, we are using the initialized network, so which gives us the random weights right here, okay? And after that, we take those random weights and we substitute it in a forward pass with our image, and it gives us the equations for our layers. Then we substitute those weights and the labels, those weights and X, whatever we put in here with the weights and X, and we're gonna add Y, and we're gonna add these equations and a learning rate, which is gonna give us the weights which are trained. Now these weights have been tuned. After this block runs, okay, and we have like good training, the weights we're left with are the weights which are trained, okay? We say the weights are trained, weights and biases, those are the actual variables which are like properly trained, okay? So we use those variables with X to predict now, okay? So that's what these blocks are right here. So we're gonna take X, any X, okay? And we're gonna use those weights and biases to predict the label for that particular X, okay? That's how it works. So yeah, we did all this to find the actual weights. We started with random weights, which gave our network, which classified the images incorrectly in the beginning, but slowly it learned through back propagation, and now those weights have been adjusted to clearly classify the images. And let's see. And then we can, this is just the training accuracy, okay? And after that, we're gonna take the test. You remember right here, we split it into X train and X test. We haven't used this data at all, so this model hasn't seen this data. So we're gonna use this X test here. Okay, we're using it somewhere. Okay, right here, test prediction. So we're using X test here to predict labels, and Y test to see how, if the image matches the labels or not. So that's gonna be fun. We're stuck at 80%. All right, so we have a training accuracy of 80%, learning rate of 0.1. Okay, let's make some test predictions. All right, so let's see here. So it classified, this is on test data, it hasn't seen this data before, so we fed in this image with the label 0, it predicted 0, that's good. And for this, it predicted 0 as well, that's sad that we had. and label is 7. It predicted it as 1, but we can cut it some slack. It looks like a 1, to be honest. And for this, it predicted a 5 for a 5. Okay, these are some random numbers that I took, so there's random indices. And let's see what the accuracy is. Okay, the accuracy is similar to the training. It's 80%. So if you tune these parameters right here, you can tune these, like number of nodes per layer, or you can change the learning rate to get better accuracy. Okay, so you have to keep experimenting. Not only that, you can change these activation functions. I've used ReLU, and sigmoid, right? There are a lot more activation functions. And not only that, right here, we used cost function as the mean squared error, right? We can use cost entropy. There are a lot more loss functions as well. So you can experiment with all those to increase the accuracy of this particular problem. So that is it. Congratulations, now you know how a neural network works from the ground up. So this is behind everything that's booming right now, every ChatGPT transformation. So we inputted an image, right? So what if we had a video? Video is nothing but a series of images, okay? Frames, series of frames. Each frame is an image, and each image has pixels. So that's how we'll feed it. The thing with ChatGPT, Claude from Anthropic, and Llama 3, all those are transformers, and they boomed because, you know, we can do that for pictures and like videos, but they found a way to convert sentences into tokens. Okay, hope you're fascinated by the topic. And oh, by the way, this is the last time I'm gonna code anything from scratch like this. I'm going to be using the advanced frameworks like TensorFlow and PyTorch moving forward. This was just like an educational thing. Hopefully you have an idea, not just an idea, like you have a good understanding of what a neural network is. All right, that is my time. Hope you enjoyed the course.